So K can usually be obtained by simply dividing the solubility of A by dividing solu of A in Sx by A in So. Okay, so if we wanted to find K for benzoic acid in, well, let's keep reading because there's the thing about the base, which I didn't get. So Fa is defined as the fraction of A remaining in the original in grams or in concentration. Oh, after N extractions. Using a constant volume of an immiscible solvent Sx for each extraction. Thus, the amount of solute remaining in SO remaining amount of remaining in SO after one extraction. 5.3. Okay, wait. I need to work through an example, dude. Let's keep reading, but I need to do an example. The amount of solute remaining in SO. Wait, okay, let me just work through an example first of this. If K is 2, if K is 2, and we currently have, let's say, I don't know, just 10 grams. 10 grams of benzoic acid. K is 2 for water as the extracting, and let's just say what is it, diethyl ether is equal to S original. So then to get K, we really need to know the solubility of so it starts out that the benzoic is dissolved in the original, which is diethyl ether. And dissolved in, let's just say 10 milliliters of diethyl ether. So the concentration is just going to be 1 gram per milliliter of benzoic in ether. Okay, that's cool. And what we want to know is, well, so let's, okay, and we assumed K is 2. So now we're going to add 10 milliliters of water. So the solution, the total, S total is 20 milliliters of half and half. Now, K is basically going to be K is equal to the concentration of A in S extraction over the concentration of A in S original. So this is equal to 2. So let's expand it out to use this. So, yeah, so the grams in A in grams of SX over A or SX volume, VSX. And then we're going to be dividing that by the concentration in the original. So this is going to be the grams in SO. And this is going to be the volume of S original. So the volumes we know. So these, since we're using an equal, these cancel out because this is 10 milliliters and this is 10 milliliters. So then we're going to get, A GSX over A GSO is equal to 2. And we happen to know, so let's call this, I don't know, X, and let's call this Y. So X over Y is equal to 2, and we know that X plus Y is equal to 5 grams. So then we can just do the math. X is equal to 2Y, so then 3Y equals 5, Y is equal to 5 over 3. So then the grams of A in SX is going to be equal to X, which is going to be 10 thirds grams, which is about 3 grams, 3.3 grams. That makes sense. So you still lose a lot, but I don't know what the K's are actually going to be. Okay, yeah, but that's actually a good point. Is then we so now what we're gonna have is we're gonna have Y grams in SO, and it's still gonna be 10 milliliters of ether. And so we can do a second extraction. So now if we do a second extraction with 10 more milliliters, we're gonna have X over Y is equal to 2 still. And because the volumes we're still doing 10 milliliters, but then X plus Y equals it will but this is No, it's just going to be 5/3. Yeah. Okay, so we can just do the math then. X equals 2y. 3y is equal to 5/3. Y is equal to 5/9. So x is equal to 10/9. So we can get, so then our total, running total is going to be, what is it? It wasn't 5/3, it was 10/3. Yeah, 10/3 plus 10/9, which is going to be equal to 30/9 plus 10/9 is equal to 49, which is what? 4.44 grams. Okay, so how did they get this equation? So let's just do the extraction. So um, and let's do it actually in just say k is equal to 2. And then so what that means, and then let's just say that uh, so we'll have V VO is equal to 10. And actually let's use maybe, I don't know. For now, no, but maybe later. So this is, so K is what is really, K is the equilibrium value for the concentration of solute A in the extraction solvent divided by the A in original solvent. Or I guess, but and then it would be the concentration in extraction solution, since A, the part of A may increase. Does it? Error is usually negligible if the solutions are dilute. K is also approximated by K is also approximated by just dividing the solubility of A in Sx, which is the extraction solution or solvent, by okay. So can we actually look that up? We're still here, but I just want to, because it's like I've been watching these chem videos and they do extractions all the time. And I feel like if you don't just go through this, then you're never going to really get extraction. So let's just find. Presumably, oh, benzoic acid is oh, because it's an oic. Yeah, yeah. I was treating it like I wrote what benzol. Is benzol a thing? Uh, I was thinking of phenol. Yeah, I was thinking of phenol. Solubility in acetone, solubility in ethanol, methanol, olive oil, 1,4-dioxane. So they do give lots of solubilities. I mean, that's pretty cool, but we need to find the one that I'm interested in. Solubility depends a lot on temperature and for water on pH. Okay, so 25C. Okay, so yeah, solubility depends. So this is at 25C. In water, oh, it's extremely low. Wow, it's like really low. 3.44 grams per liter. It really does not dissolve in water. And why is that? You would think it would, right? I mean, it's pretty polar. What's its pKa? Where's the pKa? 4. Does this stand for dimethyl sulfoxide? What does this stand for? Yeah. Yeah, I was looking at that yesterday. So it's a pretty, I mean, as far as weak acids go, it's pretty strong. 4, 10 to the minus 4. I always have to unwrap exactly what that means. So if we go to here, we just go here, let's just say using chem. We should be able to do this, right? And I guess what I want to know is for a pKa, so now I want to take a pKa and get the Ka. So that would just be inv p, right? Yeah, so let's just say the pKa is 4.2. Was that what it was? Let's just do this too. Export p inv p conj p conj Henderson Hasselbalch conj p inv p conj and Ka. I just export it all. Okay, so we should be able to do this. Yeah, we can't do that, but we can do this, right? What? Oh, you know what happened? Because it doesn't default to the right thing. Like, why wouldn't it default to the current? Anyways, what we want is inv p of pKa, and that's going to be, 10 to the minus 4.2. And this tells us the Ka. And Ka, if you have Ha plus H3O, or no, H2O, goes to A minus plus H3O plus, then the Ka is equal to the concentration of A minus H plus over HA. So the concentration of A minus times H plus. That's the thing about weak acids is they are really weak. Like they basically don't give up their protons. Okay, so let's just like track through this. So if solubility of benzoic acid in water, 25C, pH 7. And let's do this. You always gotta have units. Is that right? Quantities. And this is gonna be U grams per liter. And so then if BA water, pKa BA water water is equal to 4.2. And the units of pKa's, because the Ka is going to have a unit of apparently, okay, so apparently I didn't know that. Ka's are unitless, and so are pKa's. So pKa is unitless, so that's fine. So now what I want to know is what is the answer. The question is, what is the concentration of H plus in the water in, let's say, 10 milliliters of water? So I should be able to just do SBA water times V water. What? Oh. And this is in kilograms. And that, but then to determine the, hold on, I'll be right back. Okay, so now we need to do some sort of like, so we need to figure out, we know the ratio A minus H plus over HA. And let's say we add, let's say that 10 we're, well, okay, yeah, I mean, it doesn't matter. Let's just say, let's say we have 10 grams. This is good practice because just doing this over and over again, man, like, you got to get comfortable with this. So 10 grams of BA added to 10 milliliters of water. I mean, actually, we know it just from this. From this. This is how much it is. So you should be able to do this, right? Okay, good. So 34 milligrams. Okay, so now we know we have 34 milligrams of BA, which is basically HA. And then we have 0 and then 0. And I've always gotten confused by this because just as a baseline, I'm pretty sure that the concentration of H plus in neutral water is 1E minus 7. You know, Gen Chem, they don't stress enough that you really need to understand acid-base chemistry. But yeah. Um because if you have H2O dissociating into H3O plus OH minus, then you get the KW, which is H plus OH minus over nothing, which is equal to. And how do we know? And how do we know that the KW is 1E minus 4? Oh yeah, it was right here. But okay, so then what's next is we want to now know what the concentration of. So we can definitely assume that the initial concentration of A minus in the water is 0 because we never added anything to it. For the initial, then the change, then the. I'm gonna do the ice table thing, but we know that H plus is already 1E minus 7. That's a given, but I don't know if you include that. Usually they kind of hand wave it away. Oh yeah, you need 2. Oh, I forgot all this stuff. Okay, so we should get um, x times x plus 1e minus 7 over okay, so we should get this. x times x plus 1e minus 7. Or actually, let's just do this. That's fine. Divided by 0.034. Actually, let's... this is a concentration, right? This is a concentration. They're activities, though. Let's just do it unitless. Minus x is equal to Ka, or let's say pK. We can get rid of this stuff. And at this point, is that right? I mean, I want to know about this, but let's just do this. I really wish they had a dark mode for this because it's so bright. Okay. Oh, no, no. 10 to the minus. Then, yeah, the mass of this is going to be equal to the solubility times the volume, which is going to be in grams or kilograms. Perfect. I like how it formats it. So now what I want to make is the expression here. Can I do that? I don't think I can do that. How do I do quick scientific notation in? Okay, one. Okay. I know I can just write 10 to the minus 7, but E was faster in Julia. Anyways, so now we're going to get... what if I do... Can I just do... What if I do N of... Does this strip the units? Bro, how do I disable that? I hate that so much. Wait, is that the concentration or the amount? Yeah, okay, so wait. Let CT be the total analytical concentration of dissolved benzo species. Oh, okay, all right. So first, so this gives us the molar solubility. Basically, the otherwise no, the saturated concentration is 0.028 molar. Yeah, because okay. So this is wrong because to use Ka we need the quantity in the expression to be concentration, not mass. So in that case, the um, um, so then here we need to use CPA water. Okay. So Oh. Oh, that makes it more confusing. Sometimes SBA could be equal to the concentration of HA and A minus. I see. Most handbook solubility and water numbers are effectively total dissolved benzoic species at equilibrium in plain water. Your mass balance is already the right. What is H? H is the okay. I don't get that, but this one is close enough. So now we need to find the concentration, which is going to be uh, SBA water times molecular. How do I get that? But it's not in units. Let's try this. That's so cool. That's actually so freaking cool. Let's do this. This is probably right. There we go. Was that right? Did I get the right answer now? — 1.6. Okay, I didn't get it right still. X times this, CT minus this. That should be right. Oh, but this is, oh, okay. So this is concentration A. So now, oh, interesting. Okay, yeah, let's see this. Wait, but is that's not a thing. Dude, that's so cool. It's like suggested in the, wait, but just benzoate. That's kind of lame. So it knows it's a ion, but it doesn't. That's lame. See, it's like almost amazing. 121. Yeah, okay, yeah. Okay, so now we have, 1.3 millimolar of A. And then, so this is going to be, millimoles per liter. And then we want to multiply by 10 milliliters. And then we'll have moles. And then we want to multiply by the molecular weight of A. All right, so here we can do this. So let's just take, I think you do have to do to get the number. Oh, do you have to do? Oh no, it's slash dot. Okay, and then so now, but this isn't in. So we should be able to make this quantity in. Bro, that's so annoying. Okay, so then it's Ca times V water times weight of A. Okay, nice. And we finally get 1.6 roughly milligrams of A minus. Which is, we can approximately say that we have 1.6 milligrams of H plus also. All right, so let's get on with it. So now we know so what have we done? So we took the solubility of the benzoic acid in water and the solubility in the diethyl ether. But we didn't really, did we do that? We didn't really do that. We need to go back up. The solubility in the diethyl ether is like really high. One oxybisethane. What kind of name is that? Okay, so we have the two solubilities. So we should be able to just get the K. We kind of did a long-winded thing because we wanted to do the concentration of so the concentration of I mean, yeah, we would just do the so the original is ether, right? So the concentration of A in ether. If we wanted to saturate it, Yeah, because if we, this is the solubility. So if we put less than that, so like let's say the maximum that we could put in this, so this gives the cons of A in so if we wanted to find the let's see, what am I trying to figure out? I want to find the maximum amount of, I would just divide this by 100. So the most, so if, for the sake of whatever, let's just say V ether is equal to V water. And then we could do SBA ether times V ether. So the most BA you can put at, you know, whatever it is, 25C in 10 milliliters of ether is 10 or is 2.4 gram, 2.14 grams. So one thing we can do is just do K is equal to the solubility of the extraction. So it's SBA water over SBA ether. This is unitless, which is good. And so basically this shows that the, you know, at present, the extraction, it's terrible. It's like, yeah, it's terrible. Okay, so now we need to do but in any case, so we know this, and we know we're starting with here's a pen. We're starting with how many what did I originally do? 5 grams in 10 milliliters. Yeah, no, I did 10 grams and 10 grams. It's too much. Let's say with 1 gram of BA in 10 milliliters of ether. So now V ether stays the same, right? Good. So what we know is K. So K is going to be equal to A X, concentration of A in X over concentration of A in O, which is going to be equal to the mole. You could do grams too. Grams in X over Vx times VO over GO. So what is known if we decide to do extraction volume equal to original, and these cancel? So we're going to get GX over GO so GX over GO is going to be whatever this tiny number is, K, 0.016. We also know that, so now, so the equations are GX plus GO is equal to MVA. We also know that GX over GO is equal to K. So then we have to solve those equations. And you should be able to get so then K or GO K plus 1 no, what am I doing? There's gonna be GX plus, oh no, yeah, that's right. You're gonna get KGO plus GO. Okay. So we have 1 gram and V water. So that's the original. And we're extracting it in water. Do we have K? So what is this? What is that? Why is that defined? Okay, whatever. Did I define it? I'm not gonna go through the whole thing, but I think we get it. But now we need to do the nested thing. So let's just do it all here. So we should be able to reduce it to, this is always going to be the case. So we should be always able to do, so geo, give me my MBA over K plus 1. So we have K, we have MBA. So MBA divided by K plus 1. Nice. So we have almost a milligram in the original. No. Oh no, this is kilograms. Hold on. Okay, so it's pretty much all in the original. And then we can just find GS by okay, so we need K. We need V. We need the volume of the original, the volume of the extract. We need the, and I think that's it, right? Because then, oh, and then you need the mass mx, right? You need the mass or mass in the original. So it's like K is the partition coefficient, usually calculated by the solubility of the compound in the extraction solvent divided by the solute in the original solvent. VO is the volume of original solvent. VX extract solvent volume. MO is mass of uh uh Okay, so this is basically it. So then we're gonna get so first off, let's this is kind of the derivation that needs to go in here. So it's just oh well, I guess we need to do if we okay, but this is only if there, but otherwise we just need to do, let me do it on paper. This will be easier on paper. So we have gx over vx times k is equal to gx times vx divided by vx over vo v go. Okay, so then we're gonna get like vo vx times gx go. These are known or basically decided by the protocol. You kind of get to choose that. You kind of get to choose. Yeah, you get to choose all of these things, but then this is just scientific data. Okay, so then we're gonna get this equation: k is equal to vo over vx times gx over go, and gx plus go equals m. So then if we want to solve, we're going to first do kgo times vx over vo is equal to gx. So we need to substitute that in. So we're going to get kgo vx vo plus go is equal to m. Oh, it's going to be k vx vo plus 1 is equal to m. So go is equal to m over k vx vo. Oh yeah. That's definitely true. Okay, nice. So let's do a test. Or let's do the case where I did, where this was 10, this is 10, this is what I did. Okay, so that is, I think, what I got, because I got, yeah, 10 thirds was MO, I think. Yeah, y was equal to 5 thirds? No, I did something wrong. Oh, because I changed it to 5 grams. If this is 5, then I think I get the same thing. Yeah. And then the 10 thirds. Okay, so I pretty well understand this, I think. But now we want to nest, right? Because now we want to take the... Let's just do this really quick. K, VO, VX, MO is equal to 2, 10, 10, 5. I got that. Let's see. But what we want to do is say that GOGX is equal to this. But now we want to do another extraction. So we want to partition same K, same VO, same VX, except now we're doing GO. You know, and then we do this, you know, so this is gonna be GO1, GX1, GO2, GX2. Okay, then like, you know, the partial, or the amount extracted, GX1 plus GX2. So, you know, and then the fraction gonna be so we've extracted it, you know, in so if we combine them, the concentrate, so it's going to be GN grams grams per milliliter, I think. So how many is that? So it's pretty low. So you have to concentrate it. So you need to then need to remove the solvent to not purify it, but to get it out. Okay. You could give an array, but I don't want to get that far into it. I just want to understand. I don't know. I just want to do this simple one. So first, you're gonna need the K, you're gonna need the VO, you're gonna need the VX, and you're gonna need the MO. Then you're gonna need N. So first off, we're gonna have it's gonna be what's the order yet? GOI GXI is equal to partition K VO VX MO. But we can't do this because we need to start off with we're gonna say that like that. I need to think about it. Yeah, that's true. Okay, I actually get this formula now. This formula makes sense now because this is the fraction. Oh, wow. Okay, now I get it. Yeah, you can take okay, so then you can also do okay, so then just take F equal to 1 over K, and this is like this. K VX VO plus 1. Then GON is equal to MO FN Okay, so yeah, so here now you can get this, which is great. And then the total extraction is this. So now so yeah, so I want that too. So uh 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 so uh so all we need there is K VX VO and N. Or actually wait, let's do this. Extract frac will just be inv of K times Vx over Vo plus 1. Then repeat extract frac is N will just be to the N. then we can just do like MO times this is going to be the so we should be able to just do so wow, we really do. If you do 10 extractions, you basically can get all of it if the K is good. You know, what if the K is like what we actually found the K to be, which was what happens now? So this is like, wow, if K is equal to 2, you can basically get everything. I mean, yeah, why don't we just do this? Extract frac uh, K water ether 10, 10, 10. You still get, that doesn't seem right. This K water ether is so low. You get like, wait, what? Oh, yeah. This is not the extract frac. This is the remain frac. Oh, yeah. That means that with enough time you could get it, but then you gotta get rid of all the water somehow. But this is a good exercise because it shows that you really can get it out. Like, you can do it. It's just gonna take a long time. Oh, so what's the... So wait, once you add NaHCO3, all right, that was really insightful. So I understand uh this. I think it might be the same formula. Because if VO, if this is this, and this is, so they said 5, so then that's going to be 1 over 6 to the n. How'd they get 116? Yeah, I figured that was the same expression. So wait. Use it in my program. So k times 1 plus 1 is not right. But k is 5. But that's 1/6. Oh, but the volumes aren't. Yeah, you get 1. Yeah, oh, that's what I was saying. Okay, but the volume's actually 3 to 1. So then you're going to get, 3k plus 1 1 over 3k plus 1. K is 5. 1 over 16. Okay, that makes sense. Yeah, but then there you get... Okay, that all makes sense. That's good. Repeat, remain. What? Oh, because I need a... I need a... Okay, good. Should have done this whole thing. Okay, cool. Just like a bunch of duplicate garbage functions, but at least it makes it somewhat easy to figure out. So now you can do, same thing. Repeat, extract, frac. Yeah, and you get 15% of it. But what if you do like 1,000? What if you do? What if you do like 100,000? That's pretty cool, actually. You can do even if the K value is not in your favor, you can do a ton of extractions and still kind of get it out. Obviously, there's a limitation on doing it that precisely because there's probably error incurred in each extraction. So you can't really do it, but They build and fit a distribution model of for the real system. So distribution coefficient for, so is that what we're, what is dimerize? That's kind of interesting. Dude, chemical engineering actually sounds pretty sick. This seems fun. Especially if you had an automated lab, dude. I would fucking eat up an automated lab. People, everybody I talk to is like, yeah, I don't really think automated labs are that cool. Dude, imagine if you could like play around with this stuff and not have to like fucking sit around twiddling your thumbs with the actual extraction. Doing the actual extraction is so messy, but planning it out is fun. What is that? Oh. Should we look up YouTube videos? This seems like the type of thing where industrial extraction. That's actually really funny that it's why is it all cannabis? That's weird. Yes, but this doesn't go into industrial. Yeah, this is kind of, oh wow. Yeah, these guys would be the ones to do it. Oil refining.
Good morning, everyone, and thank you for joining today's webinar, Introduction to Liquid-to-Liquid Extraction and Solvent Extraction Columns. My name is Mauricio Villegas, and I am a Business Development Manager here at Koch Modular. We have a lot of material to cover today, so I will make our Koch Modular introduction really quick so we can get on with the webinar. Just want to give everybody just a little bit of background on Koch Modular. We are a joint venture with Koch Litch. Many of you may have worked with Koch Litch in the past. We have over 40 years experience delivering complete modular process systems to the chemical processing industry. Our capabilities and expertise revolve around process engineering, pilot plant testing, and delivering modular process systems. From a process engineering perspective, we pretty much specialize in complex distillation, liquid-to-liquid extraction, gas absorption, and thermal design. And we also can test those out at our pilot plant located here in Houston, Texas, which Don and Brendan will be speaking a little bit about today because they use that pilot plant when they scale up their processes. And then ultimately, we deliver all our projects modularly. We don't stick build anything. Everything is delivered by truckable module, and they're about 90% complete that way. Everything is fabricated.
Bullet points. The first one being when you have high boiling organics in an aqueous stream, and the second one being somewhat similar when you have non-volatile components in an aqueous stream. It's in those cases, it's very
Okay, so we should just keep a move on. Let's get to the acid-base stuff, because, all right, so we got this, we got that. That all makes sense. From these calculations, it is clear that multiple extractions become increasingly important as the value of K decreases. With improved recovery, so this is like a real intro to extraction, because extraction, apparently the partition coefficient is not constant. Apparently it depends on a ton of stuff. It's the wrong one. Oh, interesting. Countercurrent, bro. It's like freaking fish gills. You do countercurrent exchange. That's crazy. Oh yeah, you got to worry about emulsions. Mass transfer limits. That's interesting. What's ChemCAD? That sounds cool. These websites are always so dumb, bro. All right. Okay, but this is kind of like the advanced extraction stuff. We're just going to keep going. Selection of the appropriate extracting solvent is obviously a key for successfully using this technique to isolate and purify compounds. And important guidelines for making the correct choice are summarized here. Yeah, I mean, if you really want to model it, not just like, oh, it's crazy. Complexity is really high. The extracting solvent must not react in a chemically irreversible way. Oh, this is with the acid-base stuff. This is really important. The extracting solvent must be immiscible or nearly so with the original solution. So if you were to draw a graph, you have three compounds. You have that are all liquid in liquid-liquid extraction. You have the compound C, you have the SO, and then you have the SX. And basically, immiscible means that the solubility of SO and SX in each other is 0. The extracting solvent must selectively remove the desired component from the solution being extracted. That is, the partition coefficient of K is high, and the partition coefficient. Oh, okay. So imagine that you have C1 and C2. You want the K C1. You want the K1 to be high, and the K2 low. That's interesting. That's super cool. The extracting solvent should be readily separable from the solute. Yeah, I mean, that's a given. Use of a volatile solvent facilitates its removal by simple distillation or some, I don't know, evaporation or something like that. I guess that is distillation. We haven't done any distillations yet, which kind of annoys me because I really I think my favorite procedure is when those people, they do beautiful distillations. That's my favorite, man. I really like that. Switching out the collection chamber or whatever. That's so cool. The discussion of section 5.2 focuses on partitioning one substance between two immiscible solvents. Now consider what happens if a mixture of two or more compounds is present in a given volume of solvent SO and an extraction using solvent SX. If the partition coefficient of one component A is significantly greater than 1, and if those other components are significantly less than 1, the majority of A will be in SX, whereas most of the other compounds will remain in S0. But yeah, it gets more complicated because you're still going to have some C2, or what do they call it? B? They don't name it. C2 in S in the extraction. Yeah, it becomes harder. It definitely becomes harder. Physical separation of the two solvents will give a partial separation in this. Mm. Oh, wow. Okay. Carboxylic acids and phenols. Where's 1 and 3? What? Oh, carboxylic acid and phenols. Unless they contain fewer than about 6 carbon atoms, such compounds are generally insoluble or only slightly soluble in water because of the hydrophobic properties of the carbon containing portion, R or aryl. They're soluble in common organic solvents like DCM or diethyl ether that have at least modest polarity. Like carboxylic acids or phenols dissolved in diethyl ether will remain largely in that phase when the solution is extracted with water. Oh, thank you. How's Megan? Because 2 and 4 are salts, the conjugate base is highly polar and the K changes. Thus, the conjugate bases of organic acids may be selectively extracted from an organic phase into an aqueous phase. If the basic extract is then neutralized by an acid such as HCl, the conjugate base 2 or 4 will be protonated to regenerate the organic acid 1 or 3. Because the acid is water insoluble. Oh, it'll appear as a precipitate. Bro. There's so much going on in here, but it's actually insane. The desired organic acid may then be recovered by filtration or separation of the layers. I forgot about this. So yeah, you can do like wait. Yeah, HA. So reaction 1, HA goes to A minus plus uh, H plus. Okay, so then the KB reaction. So this is Ka. Everyone knows Ka, but KB is, I always forget the reaction for KB. So KB, you have A minus goes to HA plus OH minus. So in this case, so if we add these to if we add these reactions together, they cancel out completely. Or not exactly. Oh, you can just do that? Log 10 Ka of HA